Hello and welcome to video lecture number 26, which covers section 6.1, day 1, counting with combinations. By the end of this lesson, you will be able to count the number of possibilities in a given scenario using combinations. So the first question you should have is, what are combinations and how do you use them to solve counting problems? And more specifically, which type of counting problems can they be used in? Let's take a look at example 1. So suppose Tony's Tasty Pizza is offering pepperoni, ham, sausage, onion, olives, and mushrooms as toppings you can put on a special pizza that is going for a temporary promotional price. So suppose you want to order a 2-topping special pizza. The question is, how many ways can this be done? Or in other words, how many pizzas are possible? And Tony's Tasty Pizza might want to know this so they have some data for their sales and cost operations. So if our goal is to determine how many different pizzas are possible in these scenarios, we need to consider the numbers and options given. Well, we have 6 total toppings to choose from, and I've circled those in red, and we're only going to take 2 of those at a time on the pizza. Now, there is an additional scenario that says we cannot double up any topping. So for instance, we can't have pepperoni and pepperoni or ham and ham, etc. So assuming I have no other way to figure this out, I'm just going to make a simple list, and I'm going to do so with a list/tree diagram, so sort of a visual as opposed to just listing the items, which you could do. So let's see if we can come up with the answer to this before we actually move on to some formulas and things that might help us. So I'll start with pepperoni. Now, I want to consider what are all of the possibilities I could put together with a pepperoni pizza. So remember, we choose 2 toppings. So that means pepperoni could be used with ham, it could be used with sausage, it could be used with onions, olives, or mushrooms. So this gives me 5 possibilities so far. Next, I'll move on to ham. Ham can be combined with any of the other 4 remaining toppings, sausage, onions, olives, or mushrooms, but we cannot use ham and pepperoni again since we've already counted that possibility. That would be the same pizza. So let's continue this pattern and see how many total possibilities we have. So here are the rest of the possibilities, and so let's count them. So with the pepperoni, remember, we had 5 options. With the ham and its possibilities, we had 4. Yes, there's a pattern here. Then we moved to 3, 2, and 1. So our final answer to this question would be 5 plus 4 plus 3 plus 2 plus 1. And that means there are 15 different pizza combinations we could create under these situations. Now, there are shortcuts and other ways to figure this out, so that's what we will lead into for the rest of the lesson. So the Tony's Tasty Pizza example from above could also have been solved using combinations. Combinations are defined to be a group of R items chosen from another group containing N total objects in which the order of selection of R does not matter. We commonly refer to this as N choose R. So there are a few ways that you'll see combinations symbolized, and the first one is just parentheses with the N value on top and the R value on the bottom. So recall that N, the top value, will be the total number of objects in the larger group, and the R value will be how many of those objects are being taken each time. Another way you'll see it written is an NCR, and that's the same thing as what we wrote first, just again another way to write it. So let's talk about how the formula is calculated. So here is the actual formula for combinations calculation, and notice you see 3 exclamation marks, and this may or may not be the first time you've seen that, so we need to discuss what that means if you're going to be able to use this formula. So the exclamation marks are pronounced as factorials, and that means to multiply the number in front of that exclamation mark by all positive integers that are less than that value. So I'll show you some examples, obviously, in example 2. And the last note for combinations is when you're using this counting method, if you're going to use this formula, it can only be used when the order of selection is not important and when you cannot repeat an item, meaning you can't select the same item twice. So both of the answers to these questions are no. So example 2 asks us to write how we would read each symbol and then to calculate each combination value. So in example 2a, we have 8C5, and that's pronounced as 8 choose 5. In other words, we have 8 total items, and we're going to select 5 of those items and create groups with those 5 items. And the question is, how many different groups of 5 could we create? So I've plugged in the net values for 8 and 5 into the combination formula, and now I will simplify. Well, we still will follow the order of operations, and I would simplify 8 minus 5 in the parentheses in the denominator. So when I simplify 8 minus 5, I am left with 8 factorial over 5 factorial times 3 factorial. So let's discuss what 8 factorial, 5 factorial, and 3 factorial even mean. So the numerator, 8 factorial, would mean that we're going to multiply 8 by all of the positive integers that are less than 8. So that would be 7, 6, 5, 4, 3, 2, and 1. Now, 5 factorial and 3 factorial follow the same pattern. 5 factorial would be 5 times 4 times 3 times 2 times 1. And then 3 factorial would be 3 times 2 times 1. Notice it's only positive integers. We do not include 0. Well, this is a pretty large value, and so what we're going to do is we notice that there are some values that are in common on top and bottom. So for instance, I could cancel out the 1 over 1, 2 over 2, and 3 over 3. I could also then cancel out this 5 over 5 here and the 4 over 4. So once I cancel out common factors in numerator and denominator, we're simply left with 8 times 7 times 6, which is 336, divided by 3 times 2 times 1, which is 6. So our final answer is 56 total combinations. In other words, there are 56 different groups of 5 that can be created when selecting from 8 objects. You'll never get a decimal answer here because, again, you can't have a decimal number of groups. We always have whole number answers. So try B and D on your own. I'm going to show you example 2C. So moving on to example 2C, we have 4 choose 1. So I'll plug the values into the formula as you see, and I will start to simplify. Once I get it to only factorial statements, I will then try and simplify those by canceling out common factors. So I have 4 times 3 times 2 times 1 in the numerator, and I have 1 times 3 times 2 times 1. Now notice in this particular case, I have 1s, 2s, and 3s that will cancel out, so my final answer is 4 divided by 1, or 4. So again, those were separate answers. So please try example 2B and D on your own and have those ready to check for tomorrow. So please try example 3 on your own, and I'll try 4 with you. So example 4 relates to the Michigan lottery game, Lotto 47, in which you get to select 6 different numbers from 1 to 47. The question is, how many different sets of 6 numbers are possible? So again, how many groups of 6 numbers could we create if there are 47 numbers that we could choose from? So this becomes a 47 choose 6 situation. Now because these numbers are a little larger, I'm going to show you how you can do combinations on your graphing calculators. So here's the sequence of keys you would press to have this pop up on your calculator. So you start by entering the number 47, the total number of objects, on the home screen. Then you hit the math button, and then you scroll over to the probability menu, which is the menu on the far right, and you will then select option number 3, NCR, and once you hit enter, you will then press the number 6. So on your home screen, this would appear as 47 NCR 6, and then you hit enter, and up pops your answer. So how many different sets of 6 numbers are possible in this scenario? Well, we have about 10,737,573. So oftentimes in real-world counting problems, it's not realistic that you will just have one calculation of combinations. Oftentimes you'll have to do them multiple times to fit the conditions. So this brings up a key point about what you can do with combinations. You can either add them or multiply them, and these come up with 2 very common key words. When you see the word "and" or it's implied in a counting problem, you need to think multiplication of combinations. When you see the word "or," you need to think addition. So those 2 key words signal either multiplication or addition, which will definitely affect your answer. So let's suppose that there are 25 students in a classroom, 10 girls and 15 boys. I'm going to randomly call on 4 people to come up to the board to answer a warm-up question. How many different 4-person groups are possible if we have to meet the following conditions? In part A, every group of 4 must contain 3 boys and 1 girl. First, we need to determine our N and R values. So there are 2 different cases here. There's the boys and the girls. So our first total N value for the boys is 15, and my R value for them is 3. I'm going to choose 3 boys in every group from those 15. And with the same reasoning, we have N equals 10 girls. That's our total number of girls. And then, of course, R is how many girls we're going to be choosing from that group of 10, and that would be 1. So let's put this together and figure out how many total groups we can have. So for the part of the group that contains 3 boys, we will do 15 choose 3. There are 15 boys. We're going to take 3 of them. And there's the key word, meaning we're going to take that combination value and multiply it by the 1 girl that we choose, and the number of possibilities there would be 10 choose 1. So we're going to take these combination values and multiply them together. So by using my calculator to compute the combination values, I figure there are 455 different ways we can select 3 boys out of 15, and there are 10 ways we can choose 1 girl out of 10. We will multiply those values together, which will give us 4,550 different 4-person groups which contain 3 boys and 1 girl. Please try example 5b on your own using the same reasoning in example 5a. The only difference is the scenario has changed in number of boys and number of girls you're choosing. So example 6 says, William Shakespeare wrote 38 plays that can be divided into 3 different genres or categories. There would be 18 comedies, 10 histories, and 10 tragedies. So in part A, suppose you plan to read 2 or 3 of them, regardless of which category they're in. How many different ways can this be done? So, since we are reading 2 or 3, we consider N, the total first, being 38 total. Now we're going to read 2 or 3, so that first of all, our R1 would be choose 2, but then second of all, our other R value could be 3. Notice we're using 38 in both cases because that's how many we have to choose from. So we will set both of those scenarios up as combination situations, and the key is the word or. We will not multiply these together, we will add them because of that word. So I will use my calculator and figure out what both of these combination values are and add them together, and we are finished. So when calculating and adding those two combination values together, we end up with 9,139 possible ways you could do this. So in part B, we have a different scenario. We plan to read 2 comedies and 1 tragedy. How many different ways can we do this? Well, let's start with the comedies. Well, how many do we have to choose from? We're going to choose 2, but there are 18 of those to choose from, so that's our N, or total object number value. And then for the 1 tragedy, there were 10 total tragedies to choose from. So our R values are exactly how many we would like to choose. So we want 2 comedies and we want 1 tragedy. And remember, this is an AND situation, so we will be multiplying our answers together. So when multiplying those values together, we end up with 1,530 different possibilities to complete this task. So I'd like you to try examples 7 and 8 on your own, but in example 7 I want to make a few changes since the Powerball lottery game and its rules have since changed. So let's make this 1 to 69, and you get to choose one number from 1 to 26. So these reflect the current Powerball rules, so we'll get a more real-world answer for number 7. So this concludes video lecture number 26. As always, take a moment to look over the examples we've done together, as well as the ones you're asked to complete on your own, and write down at least one question that you can bring to class tomorrow. Thanks again for watching, and good luck.